Okay, lads and ladies, welcome back to Calc 1. Today we don't have a whole lot of stuff to do. It's not like a big day full of fresh material, but I do want to give you the opportunity to ask questions. We can look at a handful of more areas between curves problems, and I can address anything that you guys would have liked to have done in office hours yesterday while I was at jury duty. Good news about that, it's done, it's over. Got myself kicked off the case because one of the witnesses and one of the defense lawyers are previous students of mine. So we don't have to worry about that anymore. But I imagine there are some things you guys would like to look at. And I think it's worth looking at just a handful of more practice problems. Today is the 14th. So a reminder here. Your last midterm exam, the last exam before the final, exam 3, is next Monday. And I believe the date for that is the 19th. Yeah. And it'll be like all of our other midterms, it'll be in class. It's going to cover everything that we've done since we did exam 2. So exam 2, remember, went up to curve sketching. So everything we've done since then, which is mostly antiderivative and integral stuff. I gave a list of topics the other day. So I don't feel it's completely necessary to go back through all of those, but just a quick recap. Everything since, I guess, curve sketching and optimization were the last things we did. So we're talking about antiderivatives, areas, distances, the definite integral, fundamental theorem of calculus, indefinite integrals, net change theorem, substitution, and areas between curves. Those are the topics, the sections in the book. Let's see now. There's also, where's that in here? Should be 2 instances of. Yeah, so there's this one. One other topic I really want to discuss with you guys. We talked a little bit about the mean value theorem back in the day, but there is a second version of it. So I like to postpone the full conversation. Integrals. It should be. Yeah, okay. That's in 6. Oh, it's all the way up in 6.5. All right. So I'd like to begin today. That stuff we're going to do after the exam. So I'd like to begin today with some more examples. Or homework questions. 6.1. It doesn't necessarily have to be from 6.1. If you've got a homework question you want to see from another recent homework, I'd be happy to look at that. While I go through and pick an example from the book to begin with, I would like you guys to take a look at your homework and see if there's anything in there that you would particularly like to look at. I'll get here to 6.1. We'll pick 1 or 2 more problems to look at. We've seen a handful of these. But I think it couldn't hurt to look at just 1 or 2 more. So there's 1, 2 in here. Those are with graph utility help. Number 27 here is a good problem. What is this? X to the 400. That's a little too easy. Did something like that the other day. All right, so I'm going to begin here with number 27. because the phrasing of the problem might look a little bit intimidating, and I think it makes for an interesting challenge. So I will start with this guy, and then after that, we can look at any homework problems you guys want. So, example, find the area of the region bounded by, and then y equals 1 over x. Y equals x, and y equals 1/4 x. And they add on the stipulation here that x is greater than 0. So how do we do this? We've been given these things, so we first need to graph these things. Remember, all of these area between curves problems, all this stuff from 6.1, your first move needs to be to graph these. And on the test, I will give you explicit instructions saying you need to graph the region. So this is a good opportunity for you to practice your graphing skills. And we want to draw the region nice and big. This piece over here tells me I'm focused just on stuff to the right of the y-axis. So I'm not going to draw a nice symmetric thing. I'm going to draw it like this. 1 over x we've drawn a few times in this section. Looks like this. It's a rational function. It has horizontal asymptote y equals 0, vertical asymptote x equals 0. That's what 1 over x looks like. The point here, kind of right at the vertex of this hyperbola, is 1, 1. And we know what y equals x looks like. Y equals x is a line with slope 1 going through the origin. It also goes through 1, 1. So there's y equals x. Y equals 1/4 x. This guy is a line with slope 1/4 going through the origin. So when x is 1, he would be down here at 1/4. And I think before you sketch this guy in, it's nice to see where they intersect. So remember, we also need to find these intersection points. And sometimes it can help you draw your graph if you find those intersection points first. Of course, 1 over x is equal to x when x squared is equal to 1, which means x would be plus and minus 1. And since we're focused on x's which are greater than 0, we're not worried about the -1. That's the point that I already drew right here, where x is equal to 1. But when 1 over x is equal to 1/4 x, if you cross multiply everything here, you get 4 equals x squared. And that means that x has to be plus or minus 2. So if I mark this over here as 2, that's where 1/4 x is going to smack into 1 over x. So 1/4 x also goes through the origin. Something like this. And the y value here, if you wanted it, we can find it, although it's not 100% necessary for the problem, would be the y value on y equals 1/4 x when x is equal to 2. So if I feed this thing x equals 2, I get 1/2 out. So you could, if you wanted to, you can mark this over here as 1/2. So that's the complete picture. Right, we need to begin with a drawing. And now that we have the graph, we can identify the region. There's, again, only one like enclosed region here, and it's this region. Sorry about that, guys. Okay. So here's the region whose area I'm trying to find. And remember, in these simple cases where the functions are given to us as functions of x, we want to integrate the upper function minus the lower function. So remember the area between curves from x equals a to x equals b. This is the integral from a to b of the upper function minus the lower function dx. This is how this works if the curves are functions of x, which they are here. The catch is there's not a consistent upper and a consistent lower. So I'd like you guys to tell me a little bit what's going on here. You don't have to give me a full answer. You don't have to tell me what exactly integral I need to solve. But give me some idea of how to get started setting things up. What is the strategy? What do I need to think about with this region before I can write down the integrals?
If you turned it like sideways, like turn the graph sideways, could you go right minus left? Because there's more of a consistent, never mind.
Yeah, it's a good thought, right? But there isn't a consistent right minus left either.
Yeah.
So like this guy would always be my right, but then my lefts would be this and this depending on where we are. So something going on about this point, whether we look at it like this or like this, there's something about this point that messes things up. Right? You guys see what I'm saying there? Whether you're thinking of it as upper minus lower, if I look over here, my upper and lower are x and 1/4 x. If I look over here, my upper and lower are 1 over x and 1/4 x.
Could you add the two?
Yeah, I think so. Between Mackenzie and Trevor's answer in chat there, the big thing is that we're going to have to split the problem up. We're going to have to consider the stuff to the left of 1 separately from the stuff to the right of 1. So from 0 to 1, from x equals 0 to x equals 1, y equals x is the upper, and 1/4 x is the lower. And then from x equals 1 to 2, 1 over x is the upper, and 1/4 x is the lower. So we need two integrals here. This is the idea. We're going to kind of consider these two parts separately. So if we wanted to, in the notation we were using the other day, I could split this into A1 and A2. And here the area that I want, I'll just call A, is equal to A1 plus A2, where A1 would be the integral from 0 to 1 of the upper function here, which is y equals x, so just x, minus the lower function here, which is 1/4 x dx. And A2, that would be the integral from 1 to 2 of the upper function there, which is 1 over x, minus the lower function there, which is 1/4 x dx. So this would be my kind of strategy setup, right? We need to draw the picture and then think about the geometry of the region until we can see how to get that area in terms of some integrals. Are there any questions about where either of those two integrals are coming from or what either of them represent? Okay, so let's go ahead and evaluate them. We're ready to go ahead and crunch them out. Let's do it. A1, the integral from 0 to 1 of x minus 1/4 x dx. I want to talk for a second about kind of smart approaches to integrals like these. Yeah, I could find an antiderivative for those two pieces. Sure, they're both power rule things. Should I though?
No.
No, what should I do instead? What makes more sense?
Combine them.
Yeah, they're like terms, right? This is x to the 1, this is x to the 1. It's just 1x to the 1 minus 1/4 x to the 1. So before I go troubling my head about antiderivatives, why not write that as a single x? It's 3/4 x dx. Right, if I have $1 and you take away $1/4 of a dollar, I have 3/4 of a dollar. The 3/4 can pop out. And you're just left with integral 0 to 1 of x dx. The antiderivative, or n antiderivative, I should say, for x is 1/2 x squared, or x squared over 2. This is 3/4 times x squared over 2 from 0 to 1. And remember, after you take your antiderivative, the integral and the dx go away. We should never have an antiderivative taken inside of an integral. Evaluating between bounds now, I get 3/4 times 1 squared over 2 minus 0 squared over 2. 1 squared is 1, 0 squared is 0. So this whole thing here is just 1/2. This is 3/4 times 1/2, which is 3/8. I'll give you just 1 second to think about how we're going to set up the second integral. I need to get some water off the stove. So is your teacup in the bedroom? All right. So our first region has area 3/8. And we got that by computing this integral for A1. The second region, A2, we've got room here. I'll just write it on the left side. Is the integral from 1 to 2 of 1 over x minus 1/4 x dx. Can I combine these? Are those like terms that can be combined or no?
No.
Yeah, definitely not, right? This is like x to the -1, and this is x to the +1. So even though they're both fractions involving x, I can't combine these. So I really do just have to jump in and handle these. You could think of it as splitting them up if you want to, as the integral from 1 to 2 of 1 over x dx minus 1/4 integral 1 to 2 of x dx. Or if you are confident coming up with your antiderivative for this whole thing right away, you could skip this step, right? It is possible to just see the antiderivative for this whole expression at once. But if you feel more comfortable splitting these up, that's totally fine. It's up to you. What's this piece going to do? What is the antiderivative for 1 over x that we use here?
Natural log of the absolute value of x.
Very good. This will be ln absolute value of x evaluated from 1 to 2. And then I'll have minus 1/4. This piece is the same as the other one. It's x squared over 2 evaluated from 1 to 2. So from the first guy, I'll have the natural log of 2 minus the natural log of 1. I'm going to give myself a little bit more space here. I'm not writing the absolute values because both 2 and 1 are positive. So the absolute value of those things is just those things. And I have minus 1/4 bracket 2 squared over 2 minus 1 squared over 2. The natural log of 1 is 0. So this first piece is just ln2. Because this piece here is 0. So we have ln2 minus 1/4 bracket 2 squared over 2 is 4 over 2. 4 over 2 is just 2. Minus 1 squared over 2 is 1 over 2. So this is minus 1/2. And then you could distribute the 1/4, or you could combine the terms inside before multiplying by 1/4. Either one is fine. Let's do the latter. If I want to write this as a ratio over 2, it's 4 over 2. 4 over 2 minus 1 over 2 is 3 over 2. So this is the natural log of 2 minus 1/4 times 3/2, which is ln2 minus 3/8. Isn't that interesting? I think that's interesting because we have here precisely what we have here. The contribution from this part of the integral exactly eats up the contribution from the A1. So the total area between those curves, remember, is the sum of A1 and A2, which is 3/8 plus the natural log of 2 minus 3/8. And on a good day, that's just the natural log of 2. Oh, because there's really not anything else we can do with it. So the natural log of 2 is just the natural log of 2. You could approximate it as a decimal if you wanted, but mathematicians certainly would prefer an exact answer. So the only thing you could really hope to do with ln2 is give it as a decimal. It's just a number. Kind of like if you were to get e to the 5 as your answer, right? There's really not much you can do with that. You can just leave it as e to the 5, or you could give it as a decimal approximation. But this is the exact value, whereas that decimal, the 0.69, blah, 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 is an approximation. So this really is the exact area. The exact area there is the natural log of 2. Is that answering your question, or were you asking about something else? Well, so yeah, there are some other natural logs that we can figure out, but the natural log of a whole number, the only one of those we can simplify is the ln of 1. Yeah, so like natural log of 1 is 0. Natural log of any other whole number, I would just leave like that. If you have the natural log of e to some power, then you can clean those up. So the sort of ln things we can simplify. If you have the ln of e to some power, I'll call it x or whatever. Remember, this is just x. But the ln of an integer m, we just leave this alone, unless m is equal to 1. Right, if m is an integer. So there are some things we can simplify. There are rules that allow us to split apart natural log stuff, right? Like if we had a natural log of a product of things multiplied together, we can peel those apart and then hope to simplify some of them. But yeah, for the most part, natural log of an integer, you're just going to leave it.
Will the fractions cancel out normally, or is that just lucky?
Yeah, total coincidence here. No guarantee of that in general.
Okay.
It might be fun to think about the geometry and ask why. Why did those go away? Here, I can even bump it up like this. What is it about this picture that made that happen? What are we saying geometrically? Well, if you were to look underneath 1 over x, this is not necessary, just side discussion. If you look underneath 1 over x from 1 to 2, if you take all the area here, let me put it in orange or something. How about blue? So don't add this to your drawing. Do not add this to your drawing, just a fun conversation here. That blue area there is the natural log of 2. So what we're saying is that the missing piece down here from our A2 integral, right? Because our A2 integral just measures the pencil shaded area. The missing piece of white area down here is exactly the same as A1. This piece came out to 3/8, and the piece we had to subtract out from our A2 integral came out to 3/8. So what we're saying here is that the missing just blue, no pencil area that you see me running my mouse around here is the same as A1. We couldn't have sorted that out geometrically, or maybe we could have, but it wouldn't have been simple. It's not something that happens in general. It's definitely just a coincidence here, but it is a nifty coincidence. The reason I know that that blue area is exactly the natural log of 2 is because it's the integral of 1 over x from 1 to 2, which is the natural log of 2 minus the natural log of 1, which is the natural log of 2, because ln 1 is 0. So yeah, just a cute coincidence here. The version of this problem that you're likely to see in the homework, I don't remember if this made it in this time or not, will have different numbers. So I wouldn't generally expect that to happen, but it might, depending on your RMG. Okay, are there any homework problems that you guys decided you wanted to take a look at?
Can you do number 3?
Sure, sorry, 1 second. So I think somebody in the chat wanted to see the intersection point work. So here we had 1 over x equals x. You can cross multiply and you get 1 equals x squared. I just wrote it as x squared equals 1. And then you take square roots, you get x equals plus and minus 1. The other intersection points here are over here. Well, so we just need to solve. All right, we want to look more closely at this. If you have 1 over x equals x, you can multiply both sides by x, and you get 1 equals x squared. Because we needed to know this x value here where these guys touch. We need to know the x value here where these guys touch. Finding these intersection points is what told us how to split up the integral, remember? I need to know what is the x value where this guy stops being the upper and this guy starts being the upper. In order to do that, I need to know where those cross.
Oh, so you just basically like equal them together and then you solve?
Yeah, so the way we find intersections for any graphs is to set the two functions equal to one another.
Okay.
So I wanted to find where did this 1/x curve hit this y=x curve. And in order to do that, I set 1/x equal to x, right? This is y=x, this is y=1/x. So if I want to know where those touch, I set this equal to this, and that's what's done here. And then we solve that equation. We got two solutions, but we know we're only interested in the positive one because the problem told us we're just focusing on the x's which are greater than 0. And then I did the same thing for 1/x and 1/4x. This is just because when I sketched those curves, it was clear that they smack each other, and I needed to know where. Like this too, I needed to know this because that's what told me my upper limit of integration. Right? That's what told me where my region stopped. That making sense? Okay. All right. I did hear a homework request. Was it number 6? Did I hear that right?
Oh, I asked for 3.
3. Okay. Signed out of WebAssign as is tradition. Thank you, Cengage, for hooking up our days. Oh. Oh, no. All right, yeah, so the homework set here is short because I want you to have time to work on the study guide. Number 3, this is a good example because this is a problem where we don't have the upper minus lower thing going on. So they were kind enough to draw the picture for us here. That's very generous of them. They say find the area. I'll sketch it here and then we'll come back to the document camera. Fun question while I'm drawing. Does anybody know the other name for the red curve? X equals e to the y. That has another name.
ln of x.
Very good. X equals e to the y is the same as saying y equals ln of x. All right, so somewhere between here and here. And from here, looks like this. Okay. So they told us this parabola, sideways parabola on the left is x equals y squared minus 7. And the curve on the right, they've described it as x equals e to the y, which is the same as y equals ln x. And sometimes that is a useful fact. If I gave this to you as y equals ln x, you would want to rewrite it as x equals e to the y for the purposes of this problem. The region they've shaded there is from -1 to 1. Those are y values. We've been shading on the pencil, right? I should do some more pencil. Oh, so we want to find this the area of this shaded region. And the trick here definitely is not an upper minus lower thing. Right? I don't have anything even close to a consistent upper function and a consistent lower function. Here, it looks like this blue line would be my upper most of the time, but sometimes over here, this black curve would be my upper. Similarly, over here, this black curve would be the lower just for this little bit, but then this blue line, and then also this black curve for a little bit. So no bueno. But if you turn your head sideways, or if you rotate the page, we do have a consistent upper and a lower. So the blue line up here is y equals 1. The blue line down here is y equals -1. And the trick to this is to integrate the right curve minus the left curve between these two y values. And they were very nice solving both of these for x for us, so we didn't have to do that. So here, we'll set up the integral from like y equals a to y equals b. I like to emphasize that those are y values, right, or bounds of the right curve minus the left curve. And these are always dy integrals. Now, because if you're thinking of something as a function of y, if you're kind of thinking everything as being sideways, y is the independent variable. And that means that your integral needs to be done with respect to the variable y. Okay, what is
Wait, well, why is it y and not x? Because you had to rotate it?
Yeah, because we're thinking of this as a right minus left, because I'm thinking of
Okay.
these curves as functions of the variable y rather than as functions of the variable x.
Okay. So it's right minus left, then you do y, but if it's up top minus bottom, then it's x.
Correct.
Okay.
All right. So what is my right curve here?
X equals e to the y.
So specifically, what should I put in the integral?
E to the y.
Yeah, very good. Just e to the y. And then my left curve?
Y squared minus 7.
Very good. And remember to put that in parentheses. That's a difference of two terms. We want to subtract the whole thing. So without these parens, we might not distribute this negative. And as always, we put our entire integrand in a set of big parentheses. So here's my integrand. What are my bounds? What are my limits of integration? It goes here and here. Everybody looking at the chat? Fabrice has it in the chat there. Remember their y values. This is the importance of remembering you're doing a dy integral. That means your functions need to be functions of y, and your bounds need to be y values. So the lower bound here is the y value down here at the bottom, y equals -1. And the upper bound here is the y value along the top. That's y equals +1. So this is an integral done from, I'll write it even like this, y equals -1 to y equals +1 to remind you that those are y values. And again, the core idea, if you do get lost on this, the core idea is to remember that we're really just turning our head sideways. We're thinking of it like this. If you were to come in here and think of it like this, you'd go, oh, okay, well, yeah, my little Riemann rectangles go like this. So it's going to be, this upper minus this lower. But the orientation is a little bit weird because the negative y direction is this way, the positive y direction is this way. So your bounds are going to be from here to here. The problems in the homework will often ask you to draw in a little representative strip, like a tiny little Riemann rectangle. And here that would look like this guy. And you think of this area as being filled up by a bunch of tiny little rectangles like this. And while it might not seem like an important step here, kind of the next thing we do with these is we rotate them to generate solids, and we find the volumes of those solids. And when it comes to those sort of problems, drawing in the little strip is actually going to be a really important step. So it's a good habit to get into while we're here. All right, so we've got our integral set up. We know our bounds, we know the thing we're integrating, and we know the variable with respect to which we are integrating. That means we're ready to do this. So this is integral -1 to 1. I can distribute that negative. This will be e to the y minus y squared minus 7 dy. And antiderivatives here are not terribly hard. What is an antiderivative for e to the y?
Wouldn't it be plus 7?
Oh shit, thank you. I said it and I didn't do it, right? Yeah, we distribute the negative. Thank you, thank you. Yeah, that was the whole point. I'm so sorry. Distribute this negative, this 7 becomes positive. Appreciate that, Trevor. So again, what is our antiderivative for e to the y here? Remember, we're working dy.
E to the y.
Very good. So I'll put it over here. And then I'll have minus an antiderivative for y squared. What is an antiderivative for y squared?
1/3 y cubed.
Yeah, 1/3 y cubed or y cubed over 3. You can write it either way. And what about the 7? What is an antiderivative for 7?
7y.
Very good, 7y. And a common mistake here would be to write 7x. So remember, you're doing the integral dy. That means your variable here is y. So the antiderivative of a constant would be that constant times y. All right, these are being evaluated from -1 to 1. So there's not much left to do. We just got to plug in, subtract. This is going to be e to the 1 minus 1 cubed over 3 plus 7 times 1 minus e to the -1 minus -1 cubed over 3 plus 7 times -1. And this can be cleaned up considerably, so we should do it. E to the 1 is just e. 1 cubed is 1, so that's minus 1/3. Plus 7 times 1 is just plus 7. Then distributing this negative, e to the -1 is 1 over e, so this will be minus 1 over e. Be a little careful here because we have a few negatives. -1 cubed is -1. So this piece on its own is -1/3. But it's being subtracted here. So this will make this negative positive. So this whole piece here is plus 1/3. And then there's another negative out front. So we'll have another minus 1/3. And then finally here, 7 times -1 is -7. And then this minus, when I distribute him, he'll become positive. So altogether, I have minus 1/3, which is minus 2/3, plus 7, which is 14, and then the e terms. So I've got e minus 1/e minus 2/3 plus 14. And you could combine some of these if you wanted to, like the 2/3 and the 14, but I would be perfectly happy with this on a test. Any questions here?
So since it's a Y term, like would it be given or we just have to kind of figure that out depending on like how the graph is structured?
We would have to figure it out. Yeah, and that's what I was trying to say back at the very start here, how nice it is for them to both give us the picture and give us both of these expressions solved for Y. They could have given us this one as Y equals ln x, and this one as x equals y squared minus 7. That would be a fair problem. And then it would be on us to draw this picture and on us to realize that we need to set it up with respect to the variable y, and on us to solve this for x. So they certainly can be harder, right? Like this is, I think, problem 3 from the textbook in this section. So it's a straightforward problem, but they can get much more challenging. Well, the challenge is all in the setup. So it's mostly about your graphing skills. Right, we need to draw the picture, we need to draw a good picture. And then from that picture, we need to figure out whether we're working with respect to x or with respect to y. If we're working with respect to y, then we need to solve all of our equations for x. And here they were kind enough to do that for us at the start, but that's not always going to be the case.
In general, like if we're given 3 equations to like draw on the graph, will we have to do like that first, like how you did the first example where we'll
Splitting it
have
up?
to.
In general, no, but in practice, probably. So it's definitely possible that I could give you 3 curves and then that third curve just has nothing to do with the problem, right? It's just like way outside the frame of the region. But that would be a slightly silly thing to do. So applying, you might call it lecture logic or whatever, where like, why would I give you this third thing unless you need to do something with it? So if you're given 3 curves, it's probably safe to assume you're going to need to consider 2 separate integrals, one where, because the boundary curves are likely to be different at different points.
Okay.
Probably, yeah. All right, is there anything else from the 6-1 homework that you guys are aching to look at, or any of the other homeworks that you guys are just dying to play with?
Yeah,
I was doing.
I think, Mackenzie, if you don't mind, I think Ronald actually started to talk first, but we can go.
okay. Can you do number 20, number 25 on 5.5?
Yeah, that was homework 12, right?
Yeah.
Yeah, this is a fun one. We can take a look at this. The only really special thing about those numbers is that it's e raised to a perfect square power. What we have there is something like e to the integral e to the 16 up to e to the, let's say, 25, 1 over x times the square root of the natural log of x dx, something like this. Who can help us out with Ronald's problem? Your numbers may be a little bit different, but they should all be similar to this.
U would be the ln of x.
Very good. How did you know that, Mackenzie? That's correct, but tell us a little bit why.
I mean, I was taking like U on any of the problems, like if they were in parentheses or under a radical, or if they were to the exponent.
Yeah, that's good. Kind of, we're looking for inners and outers here. So a part of this that has an inner and an outer is the square root of ln x. Or like if you look at the last guy, the part of this that has an inner and an outer is the square root of x minus 8. A lot of these have radicals, but if you come back to 22, here's one without a radical. So which part of this has an inner and an outer? Well, they kind of both do. Cos of 2x has an outer of cos and an inner of 2x. So you could start by substituting for 2x. But this guy also has like inners and outers. And most notably here, I see the sine of 2x as an inner and sine as an outer. So here I would substitute for sine of 2x. You could do this with two substitutions also. Inner and outer. Well, here this power function doesn't have an inner and outer, but this is e raised to the negative x to the 20. So your inner is negative x to the 20. So we're always looking for inner and outer pieces. This fellow right here has an inner and outer piece. The outer is the square root. The inner is the ln of x. So we want to substitute for our inner piece. That's generally a good idea, at least worth trying. Okay, what else do I need here?
du.
Yeah, good. So what is du?
1 over x dx.
Very good. 1 over x dx. And before I forget, we're going to change our bounds. So when x is e to the 16, what is u going to be?
$16.
Yeah, very good. All right, we plug that x value in here. So if I plug in e to the 16 for x here, I get the natural log of e to the 16. And the natural log of e to the 16 is 16. That's kind of like what we were talking about simplifying logs earlier. And upper bounds, when x is equal to e to the 25, u would be the natural log of e to the 25, which is just 25. So sort of plugging in the obvious things, my new integral goes 16 to 25. I have 1 over x times the square root of u dx. And I need to get rid of all the x stuff before I can do any antiderivative stuff or algebra stuff here. After plugging in the obvious piece, you take care of the differential. So I come back to this differential and I solve it for dx. I get x times du is equal to dx. And I just multiplied both sides by x. Over here they cancel. Over here I get x du. So in place of that dx, I can write x du. Everything else stays the same. Integral 16 to 25. 1 over x square root of u x du. And since these are multiplying, x is a factor of the bottom here, x is a factor of the top here, the x's will cancel. And I'm just left with the integral from 16 to 25 of 1 over the square root of u du. And the substitution is done at this step, right? Now I've completed the substitution because everything, the bounds, the integrand, the differential, all just has u stuff, no old x stuff. Questions up to here? Okay, suggestions from here. What do we do next?
Now we can kind of like take you apart. So that would be like 1/2 and then it'd be negative 1/2 because it's over 1.
Yeah. So an antiderivative for this is not the natural log of square root u. I want to be clear about that. That's a common mistake. Just because you have 1 over something doesn't mean you automatically have a natural log. The way we evaluate an antiderivative for this is using the power rule. We rewrite it as u to the negative 1/2 power du. I'll come down here next. U to the negative 1/2, if I apply the power rule to that, I add 1 to the power, negative 1/2 plus 1 is positive 1/2. Since it's u to the positive 1/2. And I divide by that power. Now, dividing by 1/2 is the same as multiplying by 2. So my antiderivative is 2 u to the 1/2. And I'm evaluating this from 16 to 25. Sure. Here, I can squeeze it in over here. When I add 1 to this power, negative 1/2 plus 1 is positive 1/2. So this would become u to the positive 1/2 divided by 1/2. That's my antiderivative step. Just following from the power rule. All right. If you're integrating a power of a variable, you add 1 to that power and divide by that new power, just like x squared becomes x cubed over 3. So I get u to the 1/2 divided by 1/2, and then I flip and multiply by this guy to get the 2. And now we're ready. This would be 2 times 25 to the 1/2 minus 2 times 16 to the 1/2. And you see now why they made these perfect square powers of e, because you're going to end up taking square roots of those powers at the end. So that's 2 times 5 minus 2 times 4, or 10 minus 8, which is 2.
You don't ever substitute the original function back in for u?
Correct. The only time we do that, the only time you substitute the original function back in is for an indefinite integral. So for a definite integrals, right, indefinite integrals by u sub, we sub back in at the end. At the very end, right, like after the antiderivative. But definite integrals by u sub we change bounds. And never sub back in. Yep. I think in high school, sometimes they teach it with these, you have a choice. You can either change the bounds or sub back in at the end and use the original bounds. It's a terrible way to think about it though, because if you rely on that, then all of your in-between shit is technically wrong, right? If you do a u sub, but you don't change the bounds, then your integral you're working on now is not equal to the integral from the previous line. So it's a big faux pas. I really wish overzealous high school teachers would stop saying that. I know I've even seen some people at Santa Fe say it, but promise me, I promise you, universities elsewhere in the world where you teach mathematics seriously, you never sub back in for definite integrals. You always change the bounds and just use those new bounds. Not only is it correct, it's also much faster. All right. Questions, comments? Anything else we would like to see or discuss here?
Do you mind going to the last example so I can like take a picture of it?
Misspell it?
Yeah.
Sure, here we are.
Got it. Thank you.
Mhm. All right, what else can I help with here, guys? I remember somebody else, I think maybe Mackenzie was about to ask for a homework problem before we jumped in on this one, or did we get both? of them?
I was just going back through like the past homeworks, and I know like we learned antiderivatives, but in like previous homeworks before we learned that, we found another way to we had a like longer way when you did like xi and all that stuff to find the integral. So on the test, do we have to do that? Because like when I was doing the study guide, I was just doing the antiderivative the whole time. I was like, oh, that was previous lessons.
Yeah, good question. So here's the deal. If a problem says to use the definition of the definite integral blah, 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 to evaluate, then you need to use the Riemann sums. Then you must evaluate the integral from a to b of f of x dx as the limit of n goes to infinity, sigma I from 1 to n, f of xi times delta x. If a problem doesn't say that, if it just says evaluate the integral, then you can use antiderivatives, i.e. FTC2. So it depends. This is something that I need to test you guys on. It's considered one of the core parts of Calc 1. I know it's not pleasant, but there are good reasons for it. All of the intuition behind evaluating integrals as antiderivatives later really does come from this. And there will be integrals down the road where you cannot just jump in with this because this thing doesn't necessarily exist for it. They're called improper integrals. You'll see them in section 7.8, about a third of the way through Calc 2. So the idea that your definite integral is defined to be this Riemann sum, and then only in some cases you can use FTC2 and evaluate it with antiderivatives, is an important concept. So this is the definition of the definite integral. And if a problem says use the definition, then you've got to do this. It's kind of like, remember on exam 1, we had two ways of taking derivatives. We could either use the limit definition of the derivative or those first few derivative rules that we knew. And if a problem says use the limit definition, you got to do it that way or you don't get points. Same thing going on here. So if it says use the definition, got to set it up as a Riemann sum. If it just says evaluate the integral, no specificity, then you're free to do it however you want. If you want to do it this way, you can, but you really fucking shouldn't. You should do it this way because it's so much faster, right? I get that this isn't fun. I get that this takes a lot of time and hands get sore and small mistakes are made and problems have to be done a few times before you get it right sometimes. But it's important that we get the practice. So yeah, Trevor asked, can we do a problem like this? Let me take something, I put a few of those in your study guide just because I know that they were something we haven't done in a while. I'm not going to do the exact problem, of course, because it's a study guide problem, but I'd be happy to look at something similar. So I think I gave you just a linear function, right? Or maybe I didn't. Did I give you something like that? Let me see. Express this as an integral, express this as a sum. Well, you might not have had any of these in the study guide. Let me see. I gave you one with a linear function. Maybe it shows up later. Do not evaluate. Here, they give you that. And scramble these in the order. Evaluate the integral, evaluate the integral, evaluate the integral. Oh, it looks like there aren't any of these on the study guide. Evaluate the sub. I meant to put one in there. Let me see. I may go back and add one. So here, let's do one. Yeah, I had one in there. I don't know what one. Evaluate integral 0 to 1 of 2 minus 3x dx using the definition of a definite integral. I think maybe I was feeling a little bit bad for you guys, and I went back and axed it because I didn't want to give you too much to do. But it is entirely possible that something like this shows up on the test, and definitely, especially since it's in the study guide when I closed it, problems that check and see whether you understand this definition. So like saying straight up compute one of these integrals as a limit, I know those take forever. I think maybe the logic here was that you just wouldn't have time on the test. But saying like, you know, here's a limit, can you tell me what this limit of a Riemann sum is as an integral, or here's an integral, write it as a limit of a Riemann sum. There are problems of each of those types on the study guide, so certainly you should be ready for that on the test. And this ability to write this thing as a limit of a Riemann sum is very important. And then handling that Riemann sum, also important. So what's going on here? But remember, we need to start by calculating delta x and the xi's. You need delta x to calculate the xi's, so we do that first. That's always b minus a over n. And n here will be a variable. We're not plugging in a particular number for n. So this is 1 minus 0 over n, or just 1 over n, which makes our xi's, which are always a plus I delta x. That's 0 plus I times 1 over n, or just I times 1 over n. From there, we know that the integral from 0 to 1 of 2 minus 3x dx is the limit as n goes to infinity, sigma I from 1 to n, f of xi times delta x. So f of x here is the function 2 minus 3x. The xi's and the delta x's are known. So this is lim n to infinity, sigma I from 1 to n. 2 minus 3x is f of x. So 2 minus 3 times xi is f of xi. And delta x is 1 over n. I'll continue down here. This is lim n to infinity, sigma I from 1 to n. xi was I times 1 over n. So this is 2 minus 3 times I times 1 over n, all times 1 over n like this. So if I just asked you to express the integral as a limit of Riemann sums, you could stop here. But if we said, then go on and evaluate that integral as a limit of Riemann sums, like find me the answer, we got more work to do. So first, are there any questions up to this step? So if we just said express this as a limit of Riemann sums, like write down the definition of this thing, you could stop here. But if we said evaluate this as a limit of Riemann sums, as we've said in this problem, if we said tell me the answer, evaluate this, but use the definition, use the Riemann sums, then from this step you would need to continue and actually figure out the sum and then take the limit. So let's see what that would look like. I'll distribute the 1 over n. Lim n to infinity. sigma I from 1 to n. And I distribute that 1 over n, I get 2 times 1 over n minus 3i times 1 over n squared, right? Because 1 over n times 1 over n is 1 over n squared.
So for the first step, you're basically just plugging everything in.
Right. Yep.
Okay.
We have to calculate the delta x and the xi's. But then, yeah, we just plug everything in, and that gets us to here.
Got it.
Now, what would I do from here? I need to figure out this sum. I have some simple summation formulas I can use. Remember, our summation formulas look like.
You would break it into two separate integrals and then evaluate I in terms of n, or sorry, xi in terms of n.
Yeah, this is the idea. So I have these two summation formula that are going to be relevant here. So in order to apply this one or this one, I need to have like a sum of 1 or a sum of a constant and a sum of I. And here I have an I and here I have a constant. So the game is going to be to split it up. So this goes back in. This will look like lim n to infinity. And then I'll have sigma I from 1 to n of 2 times 1 over n minus sigma I from 1 to n 3i times 1 over n squared. And from each of those, I want to pull out everything I can. And if you want to put this whole thing in like a bracket, you can, because we're taking the limit of that whole thing. But the big idea is I need to apply a summation formula to this. I need to apply a summation formula to this. And my summation formulas look like this and this. So first I need to get this shit and all the other shit out of these two sums. So remember, if it doesn't have an I in it, it can come out of the sum. So I'd be looking at 2 times 1 over n times sigma I from 1 to n of 1 minus 3 times 1 over n squared sigma I from 1 to n of I. Right, 2 times 1 over n, when I pull that out, all that's left in here is a factor of 1. When I factor that out, what's left in here is a 1. And here, the only thing I want to leave inside is the I, so I'm going to factor out the 3 and I'm going to factor out the 1 over n squared. When I factor those out, all that's left inside is the I as desired. Now, my first sum looks just like this. And my second sum looks just like this. So I can replace them with their equivalent. I would have to look, Olivia. I'm not sure off the top of my head. So let's finish this up and then I'll answer that and then we can finish. So the sum from I to 1, I equals 1 to n of 1, that's n. So this is 2 times 1 over n times n. And then I have here minus 3 times 1 over n squared. The sum from I equals 1 to n of I squared is n times n plus 1 over 2. And now, really, this is a problem we could have done back in section 2.6 when we first learned about limits at infinity. This piece is easy because the n's cancel. But here, no n's cancel. Well, you could, I suppose, cancel one n. But let's see what we can do. One over n times n is just 1. 2 times 1 is 2. I think the most natural way to write that second piece is 3 times n plus 1 over 2n squared. Then we can distribute the n upstairs, or you can cancel with one of the n's downstairs. Right, this n and this n can cancel. This n, because it is a factor of the top. It's really important that you see that, right? This is in factored form. So I can cancel with one of those. 2 minus 3 times n plus 1 over 2n. And by our limit laws, we could split this up as lim n to infinity of 2 minus 3 halves lim n to infinity of n plus 1 over n. I'll do the first part. Lim n to infinity of 2 is just 2. And then we have minus 3 halves times. You guys tell me, what is the limit as n goes to infinity of n plus 1 over n? Does anybody remember how we do these?
Is it 1?
It is 1. Yeah, there's a bunch of ways to think of it. The degree of the top and the degree of the bottom are the same. They're both linear. So you can take the ratio of lead coefficients, it's 1 over 1. Or you could renormalize. Remember, we have a renormalization trick. You see lim n to infinity, n times n plus 1, n plus 1 over n. That's the same as the limit as n goes to infinity. I divide every piece by n, and I get 1 plus 1 over n divided by 1. And then as n goes to infinity, the 1 over n goes to 0. So you get 1 plus 0 over 1, which is just 1. However you choose to think of it. You could even use L'Hopital's rule if you really wanted to. However you choose to calculate that limit using whatever tools you remember, that limit is 1. So we get 2 minus 3 halves, which is 1/2. So that integral is 1/2. And yes, you could have done that integral much faster using FTC2, right? Using your antiderivatives. But because this particular problem said use the definition of the definite integral to evaluate, we had to set this up as a Riemann sum. The big deal is that they come out the same either way, right? That's why FTC2 is called the fundamental theorem of calculus. It's such a big deal because it gives you another way to do this really, really hard thing. Think of it as a cheat code, right? It's a shortcut that gets you around all this work with limits and capital sigmas. But before you can appreciate the shortcut, you need to know the regular route. This is the regular route. Olivia asked, at what date do the exam 3 lectures begin? So let me take a look at that. So exam 2, what was our date for exam 2? Actually, I know, let's just look at announcements here. The exam 2 link was given. Zoom link for exam 2. So that was on March 15th. So anything after March 15th would be relevant to exam 3. Is that right? Yeah, exam 2 is that day. Yeah.
Exam 3 is going to be on Monday or Wednesday?
Monday of next week.
Okay.
So one way you guys can look at these things if you want to, I keep them all organized in playlists on YouTube. If you go to my channel and look at the playlist, here's the playlist for your class. Do it here. Then you would just need to skip ahead to anything after 3:15 if you wanted to focus just on exam 3 stuff. So 3:17, this would be the start. I can paste this into the chat. So, oh. Okay, gang, I'm going to go ahead and end the class here for today. If you do have other questions or things you want to see, I'll have my normal office hour today, and then I'll add an extra office hour or two between now and Monday to compensate for the ones we missed due to that jury duty shit. If there's anything else you want to talk about, you can't make the office hours, anything like that, send me a Canvas message or an email. That is it. Take care.
Professor, can you open up all the past 2 homeworks?
Do me a favor. So if you want anything extended, just go ahead and submit an extension request in WebAssign. That's the easiest way to do it. I'll grant those before the office hour starts.
Okay, perfect.